ATP. So hexokinase, you see this coming up a couple of times, right? That word root. So what does kinase make you think of? Kinetic energy.
Yeah.
The energy of movement, or just energy? So what do you think kinase refers to, especially when we're talking about molecules at the cellular level? What's the currency of energy in a cell? ATP. And sure enough, what have we done to glucose? How do we kinase it? We added a phosphate group to it, right? So kinase usually means something's going to be happening with phosphate. Either something's getting phosphorylated or ATP is being used in some capacity. All right, so now we have glucose 6-phosphorate. Phosphate. What do? We make glucose 6-phosphate. So what have we done? How do we turn glucose into fructose? What manner of sorcery do we use? We change the structure. We make a structural isomer. Okay, so because fructose and glucose have the same formula, C6H12O6, plus a phosphate that's still on the same carbon 6, the one that's furthest away from the carbonyl group. So that's carbon 1, 2, 3, 4, 5, 6. So we go from glucose 6-phosphate to fructose 6-phosphate. And you can see we've bopped that carbonyl group from carbon 1 to carbon 2. So we've gone from an aldose to a ketose. All right. Next thing that happens, here's a kinase again. Guess what's happening? We got to invest a little more energy in the form of ATP. So we've got fructose 1,6. I usually refer to it as bisphosphate. Sometimes it's written as biphosphate. What's the difference between biphosphate and diphosphate, if you had to guess?
Mine was what she said is 2 phosphates, but is that O supposed to be a P on the bottom phosphate group? Bottom.
Yeah. Good catch. I didn't draw it, but hopefully that's more clear. So diphosphate usually means that it's attached to the same part of the molecule, same carbon. Biphosphate or bisphosphate means you've got a phosphate here and a phosphate on the 6th carbon. So 1 and 6 bisphosphate.
So diphosphate, they both be on one.
Yep. Okay. Aldolase, or as I
I don't know.
affectionately refer to it in the other course, the other section, fructose karate chopolase. Crack, because what it does is it takes that 6-carbon molecule and makes it into 2 3-carbon molecules. And these two things are isomers of each other. DHAP is dihydroxyacetone phosphate. G3P is glyceraldehyde 3-phosphate. And if you can remember back to chapter 5, talking about carbohydrates, when we had that table that showed 3-carbon, 5-carbon, 6-carbon sugars, and aldoses and ketoses. And I said, this is going to come back. We're going to see this again, right? Does that sound vaguely familiar? Is this some imagining that I had? Hopefully not. So those 2 3-carbon sugars were dihydroxyacetone and glyceraldehyde. One's an aldose, the other is a ketose. I had those backwards. Ketose, aldose. Because this actually, glyceraldehyde, it has aldehyde in the name, doi. And dihydroxyacetone ends in O-N-E, so you know that it's a ketone. Anyway, these two things are isomers of each other. So when we crack fructose 1,6 bisphosphate in half, these are the 2 halves. G3P is the one, we're going to see this again in in a week. We talk about photosynthesis. But G3P is the molecule that goes on. Right? So what ends up happening to DHAP? Yeah, we can isomerize that so that instead of having 1 G3P, we get 2. And that's how glycolysis, we end up all of these steps are happening twice for every 1 molecule of glucose. This is where the accounting for glycolysis gets a little bit wonky. All right, so we've got our G3P, glyceraldehyde 3-phosphate, and then we have this thing, triose phosphate dehydrogenase, to get 1,3-bisphosphoglycerate. So a couple of things have happened here. What is that? It's an inorganic phosphate. It's a phosphate that's not attached to an organic molecule yet. That's part of what happens in this process, is that we're just taking phosphate out of the cytosol and ramming it onto this molecule to form 1,3-bisphosphoglycerate. We're also dehydrogenasing it. So when we dehydrogenase it, we're going to take a hydrogen off of it. Why are we taking a hydrogen off of this molecule? For what purpose?
An Na2 plus and NADH.
Exactly right. And I want everyone to answer in unison if you can. What is NAD plus?
Electron bus.
Is the electron bus. NAD plus is the electron bus. It takes the electrons to electron camp. Okay, it is a shuttler. It is a shuttler of electrons. Now, something that's confusing is that we take NAD plus, which is the oxidized form, and we add H to it to reduce it. Now, we're used to thinking of H as being H plus, right? A proton with a positive charge. But what's actually happening that makes NADH the reduced form?
It's also adding an electron.
It's adding 2 electrons.
Yes.
So NAD plus gets the proton plus 2 electrons. So that's how we go from this positively charged species to a neutral species. Because we add the proton, but we add the 2 electrons. I mean, we get the proton, sure, that's great, but we're really more interested in those electrons because those electrons have all the potential energy that we're going to harvest at the end of the story. Okay? At electron camp. Okay, so that's one of our NADHs that we produce. And that's very well and good. We also get this 1,3-bisphosphoglycerate. Phosphoglycerokinase. What do you think's happening there? So again, the kinase makes you think phosphate. Something's happening with phosphate and ATP, and we would be correct. We're getting one of our ATPs back that we invested, or actually 2 ATPs back from our 1 molecule of glucose, because everything that's happening on this side is happening twice. Everyone's still with me? Okay, good. Okay, then we isomerize 3-phosphoglycerate to 2-phosphoglycerate. This step, not as exciting, because all we're doing is isomerizing. But in this case, it says mutase. Think mutase, isomerase, basically doing the same thing. All right. But we need to get that phosphate off of carbon 3, put it onto carbon 2, in order to use enolase to make PEP. PEP is phosphoenol pyruvate. What is an enol? Okay. What does OL suggest?
Alcohol.
Alcohol, correct. So what we're doing is we're converting an alcohol, right there, see that hydroxyl group down here? And we're turning it into a carbon-carbon double bond. Now, I know a lot of you have not had the benefit or disadvantage of organic chemistry. Hydrocarbons that have single bonds only end in ane, like butane, propane, methane. If they have a double bond, they end in ene. So they go from being like ethane to ethene or ethylene. So that's what that's what enol means, is that we're going from hydroxyl group to a carbon-carbon double bond in phosphoenol pyruvate. Okay, last step to get to pyruvate is through pyruvate kinase. What's the difference between this molecule and this molecule? The biggest, most important one. That phosphate is going to be taken off, and it's going to give us more ATP. Ta-da! We did it. Okay? So, what is it that, oh, I missed. Is that the only NADH step? I guess it is. Yes. All right, so we have one step that produces NADH, but how many NADH does it produce per molecule of glucose? 2, because it's happening twice per molecule of glucose. We're also getting back twice the amount of ATP that we spent to get the process going. All right. And again, we're seeing a lot of what we talked about abstractly in chapter 8 with phosphorylated intermediates being used in this whole process. Right? Glucose on its own isn't powerful enough to make a lot of ATP. We have to pay in some ATP and make a phosphorylated intermediate. Then we need to phosphorylate it again. If you remember my analogy of saying a phosphorylated intermediate is like putting a jet engine on a bicycle, fructose 1,6 bisphosphate is a very, very potent, very high Gibbs free energy molecule. Okay, so where is all of the energy in glucose stored? How are we using that energy? What kind of energy stored in glucose are we using to make ATP? What part of the molecule is making the most ATP? Protons, the neutrons? The bonds when you break them, but when we make and break bonds, what are we pushing around? Electrons. We have that whole song and dance about redox reactions and how it's just pushing electrons around. And ultimately, that's what we're doing. We're trying to get as much energy as we can out of those electrons. All right? I feel like maybe there was something else I wanted to say about this, but I can't remember what it was. So, all right. I'm going to leave this up here, so if folks want to take a picture of this. What do you need to know from all this? Ultimately, what you need to know is that there's the energy investment phase, the energy payoff phase. We're breaking sugar. We're spending ATP to make twice as much ATP. Oh, that was the other thing I was going to say. How do we make ATP in this process? We do it by taking a substrate, taking the phosphate that's on it and putting it onto ATP, and we have a name for that, which is what kind of phosphorylation? Non-oxidative. Substrate level phosphorylation. So basically it's like handcrafting ATP from, oh, I have this molecule that has a phosphate, and I'm just going to gently pull the phosphate off and put it onto ADP and leave this non-phosphorylated intermediate behind. Which is an okay way to make phosphate, but not if you need to make lots and lots of ATP. You want to have a big corporate affair if you want to make lots and lots of ATP through oxidative phosphorylation. Nope, I do not. I'm sure it is nobody I want to talk to. So, actually,